So it's a special show, so we're going to have a special talk. So as we hinted at before at the beginning of the show, we are going to have the rapid fire burning astronomy questions answered talk. So what we have here on the backs of all of your trivia forms, many of you have submitted questions that you would hope that we would answer in a future Astronomy on Tap talk, and sometimes we didn't get to it. So actually, Major Merger went through a lot of them, and she compiled some of the most interesting so that we could answer them for you, except all of our space cadets only have 1 minute to answer that question. And so I'm going to be up here making sure that everyone keeps the time. I might just like scowl at them, but actually your question's going to be answered, so don't worry about that. But they're all lined up here on the stage, ready to go. And so first up, to give you an idea of what it was going to look like, we have our Dr. Astro, I don't know what your name is. Astro A. Lee. Aaron Lee, Dr. Aaron Lee. No, your space cadet name. That's what I meant. All of the space cadets, they're going to briefly introduce themselves, and then let's get going. So hopefully we can get this all done under 15 minutes. So ready?
Well, I will say that for the space cadets, we do have a special laser pointer that's a little mouse. You touch its nose. So if you need a laser pointer.
Yeah.
But yes, I will lead by example.
Yes. Okay, so you guys all ready? Get set. Go!
So my name is Aaron Lee. I'm a postdoc here in the department. And the question, I'm going to start with an easy one and answer, what is the bang of the Big Bang and what happened during it? So the Big Bang took place in less than a trillionth of a second and created all of space. It wasn't an explosion. An explosion requires a pre-existing space. The Big Bang was this rapid inflation that actually created space itself. And we think that happened because of nature breaking symmetry. So in the early universe, the universe was very hot and compact. And when it's in that state, the laws of nature are not unique. The electromagnetic, the nuclear forces, and gravity all behave like one single force. Kind of similar to how if you spin a quarter, it's kind of both heads and tails in this highly energetic state until friction robs it of its energy and it falls over and the symmetry is broken. That symmetry breaking is powerful. And so, if you take the fundamental forces and break them into 4 separate forces, that phase transition dumps a lot of energy into the universe, and that can actually create a universe, and that is a Big Bang. And this sounds super abstract, but this is the same sort of thing that we see when, say, water turns into ice. 0 degrees Celsius water has more energy than 0 degrees Celsius ice. It has to dump out even more energy during its phase transition. So, fundamental laws becoming distinct fundamental laws, that creates a phase transition, which creates a universe. Thank you.
Let's hold our applause until the very end, everybody. Okay, ready, set.
Hi, I am Sam Factor. I'm a grad student at UT Austin, and I'm going to ask, was there ever life on Mars? And there's David Bowie, because his song. So if you guys know the answer to this question definitively, come talk to us after the show. We'll get you a Nobel Prize. But yeah, so life on Mars has been in pop culture back since like the 1800s. In 1898, Percival Lowell drew this picture of what he thought were canals on the surface of Mars, which he interpreted as roads from like a civilization. Turned out to be an optical illusion, but it persisted in popular culture, and Marvin the Martian made it onto the launch patch for the Spirit rover, which I'm sure you've all have heard of. And the Spirit rover, its twin Opportunity, and as well as the newer rover Curiosity, as well as a bunch of orbiters, have all been trying to answer this question of, is there or was there ever life on Mars? We still don't really know, but what we have been able to learn is that the surface of life likely was habitable 3-4 billion years ago. So a really long time ago, maybe life could have lived on the surface of Mars, but we don't have any evidence of whether it actually was there or was not. So stay tuned, and maybe there will be a Nobel Prize.
Hi, I'm Emily Strickland. I'm a 4th-year undergrad, super hopefully going into grad school this next year at UT Austin. I'm going to answer the question, if black holes are black, how do we know they're there? Turns out that just because they're black doesn't mean they don't interact with matter that we can see. So we have light interactions. Since black holes are so massive, they bend space, so the light coming around them has to bend to get to us. And we can kind of measure that to a degree. Gravitational waves, which was a huge discovery just a couple years ago by LIGO. You can see right over here that in this very low contrast, maybe, when two black holes merge, as Brian was talking about, they give off a signal where they ripple space, and we can measure it using big lasers that are super precise. And of course, mass ejection, which somebody should correct me. I found both radio and X-ray images of outflows from black holes where if they take in too much mass, gas, dust, so forth, stars, then they eject it. And I don't know how it could spread across the continuum like that. But it definitely emits a super lot of energy, and we can see that and measure it, and it's really pretty also. Thank you.
Maybe you'll learn it in grad school. Okay.
Hey, I'm Yaloyan. I'm a sixth-year grad student at UT. I'm going to answer this very important question. Can you smell and or hear a fart in space? We don't want to embarrass ourselves in the space. After all the effort, we make it to space in probably 20 years. So we're going to do this scientifically. So if are you going to smell it? You're probably going to smell your own one from your spacesuit. You're probably going to hear it. But in terms of whether you're going to embarrass yourself from the other, we're going to break it down to the numbers. So per fart, you're going to have this amount of gas, which translates to this amount of molecule, 10 to the 21. That's 1 followed by 21 zeros. So assuming you don't need a spacesuit, you can smell directly in the space, and you take a deep breath immediately, which is a questionable decision. That's the amount of density you're going to get, 10 to the 19. And it turns out our human smell is very sensitive. We can smell gas molecule in 1 parts per billion, although it depends on different odors. Some odors are very distinctive, some odors are not. So consider all these numbers together, our detectability is about 10 to 11. So yeah, we can smell it, but that's basically just what we're going to experience on Earth. Very important difference in the space is the fart gas is going to quickly diffuse into the vast amount of empty space. It is likely to diffuse into a football stadium volume within a matter of seconds. So it kind of dropped down the number to 10 to the 9. So the long answer will be probably not, but why are you thinking about that? Turns out we can actually find an ingredient of the gas similar to what we're going to produce with our human body in the space. And if this massive collimated jet hits you, you might get some vibration, which might turn to some like bass, like you heard in like a pub or something. So yeah, that may be. Thanks.
Hello, my name is Ben Toffelmeyer. I'm a postdoc in the department here, and so I'll be answering, do stars really burn? And so the answer is sort of, but not in the way you typically think. So when we use the word burn, we're typically talking about a chemical process called combustion that creates fire. And that is not the process that is taking place in the core of the sun. And when we say burn, we're really talking about the core of the sun, not any of the outer layers. But even though they're different processes, they have some similarities, and so that's why we colloquially say that stars burn. So both combustion and fusion have this kind of similar formula. We have some fuel, we give it some energy or heat that creates a reaction that makes a change and also gives off energy. And that energy can go back into our fuel and create this cycle that will continue on its own until you run out of fuel. And so for combustion, we just have basically the reaction is, it's called rapid oxidation. We turn carbon molecules in our solid into gases like carbon dioxide and carbon monoxide. In the sun, we have a nuclear process called fusion, and that happens when two hydrogen particles collide and make a heavier element. So both are pretty similar, but is the sun really burning? Sort of. So, yeah. Thanks.
Hello, my name is Logan Pierce, otherwise known as Eccentric Orbiter. And I'm answering the question, what is SETI up to these days? So the first thing I want to say is that the term SETI refers to an area of research, not a specific group. There are lots of groups that are involved in the act of search for extraterrestrial intelligence as a research area. This summer, I got to intern with the Berkeley SETI Research Center, which is part of the Breakthrough Initiatives, which is a privately funded mission for expanding human reach into the universe. And the SETI arm is called Breakthrough Listen. And currently, as we speak, the Breakthrough Listen team is conducting surveys of the stars within 50 parsec radius of the Earth using the Parkes telescope in Australia, the Green Bank radio telescope in West Virginia, and the Automated Planet Finder optical telescope in California. And very soon, which is the project I worked on with them, they're going to start a survey of the 1 million nearest stars using the Meerkat Radio Interferometry Telescope in South Africa. That will be starting very shortly. 1 million of the closest stars. It's the biggest SETI endeavor in human history, so it's very exciting. And you can get involved. You can join SETI at Home, where SETI will actually take over your computer when you're not using it and use your computer to process their data. This has been going on since the late 90s. I actually had this on my computer as a high school student in the late 90s. And you can be involved in helping SETI conduct its research. Thank you.
Hello, my name is Jorge Zavala. I am a postdoc here at UT. I'm from Mexico, but I promise I have a visa, so I'm legal here. So the question is, where is the best place to build a telescope? The answer actually depends on the kind of telescope that we want to build. For example, we can see that gamma rays and X-rays and also infrared are absorbed by the atmosphere. So if we want to detect this kind of light, we need a space telescope. But we can build like radio telescope or optical telescope, of course, at this level of the city. Here, for example, in the city of Austin, you can see here the Capitol at UT Tower. And we can also build sub-millimeter of infrared telescope on the top of the mountain. So in general terms, the best place to build a telescope, we need a high altitude place like Mauna Kea volcano in Hawaii. We need a dark sky like the McDonald Observatory here in Texas, and a dry place in like the one in the Atacama Desert in Chile. And that's it. Thank you.
Hi, I'm Brian Gacious. I am a grad student at the University of Massachusetts. And so is Pluto a planet or not? Aaron, family show. The answer is it's not quite a planet. I mean, yes, it is a dwarf planet. And so you see kind of like a schematic of the solar system there with the 8 traditional planets. And the arrows are pointing to the dwarf planets. You see Ceres there first, and then Pluto, Haumea, Makemake, and Eris. And in fact, it was the discovery of Eris that put this all into doubt, because Eris was like the same size as Pluto. And they were like, either Eris is a planet and Pluto is a planet, then obviously we have like 15 planets. But of course, those don't look like the rest of the planets. And so this kind of pushed the IAU to rederive what kind of a planet is, or redefine. And so that's kind of shown on the right there. So the IAU now defines a planet as it has to orbit the sun. It has to be so massive that it's a sphere, and that it has to clear the path around it. And so this is what, like Ceres, for instance, doesn't match this because it's in the middle of the asteroid belt. And same with Pluto and all the others. It's still in the middle of the Kuiper belt objects. Of course, this definition has come into a lot of contests recently, because by that own definition, no exoplanet is actually a planet, because it doesn't orbit the sun. So they made that definition without thinking ahead of time, thinking, well, maybe there are other planets. So now that the IAU is now forced, because of Kepler, to redefine what a planet is so that other planets outside the solar system are actually planets, and they don't all feel the same shame as Pluto felt. So hopefully when they redefine it, maybe Pluto will become a planet, maybe it won't. But as of now, it's just a dwarf planet, not quite a planet. Thank you.
Hi, my name is Zilly. I'm a fourth-year undergraduate student at UT Astronomy, and today I'm answering what is the solar neutrino problem, and is it still a problem? So, short answer is no, it is not a problem anymore. If you remember the question about burning that goes on in the sun, it's actually nuclear fusion, and neutrinos come as a product of the fusion that goes on in the core of the sun. But unlike normal radiation, neutrinos are massless particles and they rarely interact with normal matter. So they just pass right through the sun, and we predict some number of neutrinos coming from the sun and going to the Earth. These things are very hard to detect, and when people first built neutrino detectors in the 1960s, they didn't find as many neutrinos as was expected. So then astronomers thought, maybe we don't understand how the sun works. But actually the answer is we don't know how neutrinos work. So in the 2000s, people proposed neutrino oscillation. So they said there are actually three types of neutrinos called three flavors, and on the way from the sun to the Earth, the neutrinos can actually change from one type to the other, and that accounts for the missing number of neutrinos, which is the solar neutrino problem. So now with these huge, expensive, nice neutrino detectors, we solved the solar neutrino problem. Thank you.
Which one of y'all asked this question? I'm Sinclair Manning. I'm a fourth-year grad student. You just saw me give the news, and I'm going to answer, how large is Uranus? So large is kind of a vague term, so I broke it down into the three measurables that we usually tend to think of as physicists and astronomers. So first, how massive is Uranus? Uranus is about 14.5 times the mass of our Earth, so that's pretty massive. If you want to think about it in terms of things like the largest terrestrial animal on Earth, Uranus is 1.5 times 10 to the 22 African bush elephants. So that's a lot of elephants that make up Uranus. If you want to think about it in terms of diameter, Uranus is 4 Earths placed side by side. But because we're here in Texas and we like to think of things in terms of Texas, Uranus is as wide as 41 Texases. Texases? Texi, plural. And finally, volume. How much volume can Uranus hold? Uranus can hold a volume of 6.83 times 10 to the 13 cubic kilometers, which basically means that you can fit 63 Earths inside Uranus. And because this is Astronomy on Tap, I had to do the calculation for pints of beer, excuse me, and you can fit 1.44 times 10 to the 26 pints of beer inside Uranus, which is just barely enough to hydrate this room. Thank you.
All right, I'm Stranger Solaris, a postdoc at UT, and the question I'm going to answer today is, why do radio astronomers build many smaller dishes instead of another big dish like Arecibo? So, as many other things, the simplest answer is the money. So, as you can imagine, it's financially and technically more feasible to build smaller antenna than a gigantic one as the one we have at Arecibo. And then the question comes down to, why can astronomers do that? The answer actually lies in an experiment that many of you may have done in Physics 101, where in the single slit experiment, the resolution or the width of the light fringe is proportional to wavelengths divided by the width of the slit. And then in a double slit experiment, where the resolution, again, the width of the light fringe, is proportional to wavelengths divided by the distance between the two slits, then you can see the width of the slit as the diameter of antenna, and the distance between the slits as what we call the baseline between antenna. And that is exactly the reason why astronomers can build what we call interferometers to achieve much higher resolution than what we could have with a single dish. And that resolution has allowed us to distinguish between a star and its planet. Cool.
Hi, I'm Dr. Boom. I'm here to talk about aliens. So what is the Drake equation? So Frank Drake was a radio astronomer, and he was looking at stars and realized radio astronomy might also detect alien civilizations that are spitting out radio signals. So, like, you can imagine, if you've ever seen one of those sci-fi movies where aliens are watching our old TV shows, this is kind of what he was thinking about, was like, are there these alien civilizations out there that are spitting out TV shows or trying to contact us directly? Could we find them? And so his question was, okay, how many alien civilizations might be out there? Because if we know that, then we can figure out what the chances of us detecting them. So he came up with this equation, which is not really meant to give us an exact number, but it says is meant to tell us sort of what are the big factors in what it would take to make a civilization that could talk to us. And so it's looking at things like how many stars are there out there, how many planets are there out there, how many of those planets can actually support life. Do those planets actually form life? Does that life form civilizations? Will we be able to detect that? Taking all of these factors into account. Some of these factors are pretty scientifically answerable. So, for example, the number of planets that are out there and the percentage of stars with planets was something that at the time we couldn't really give you a good number on, but nowadays we've figured out, oh yeah, almost every star has a planet, and there are a lot of Earth-like planets out there when you think about the mass of the Earth and the distance from their star. There are a lot of Earth-like planets out there, so it turns out we can answer those with science. Some of the ones that are a little trickier, we don't really understand everything it takes to form life, let alone form intelligent life, so that's really tricky. And then what gets really tough is talking about the philosophical questions, like, you know, how often will intelligent life form a civilization? And will that civilization want to talk to us? And how long does an intelligent civilization live before they blow themselves up with nuclear bombs? These are big questions we don't really know the answer to, and so it makes it really hard to determine this number. And basically, if you throw in our best science and our best guesses at these numbers, you can get a number from as few as there is one intelligent civilization in the galaxy, which would be us if we qualify as intelligent, and then or there are 15 million rather. There could be 15 million civilizations in our galaxy if you're super optimistic. Again, we don't have good enough constraints to really give us a number, but let's be optimistic and hope we're on the 15 million side. Thanks.
Hi, I'm Laura Akins, aka Star Party Queen. So of course I'm going to answer, where can you go for good stargazing here in Texas? So of course I have to put in a plug for our campus telescopes because I run one of them. And as you can see, we have been voted the best of Austin twice. So, you know, that's a nice stamp of approval there. Up top we have the Painter Hall telescope, which is our antique 9-inch refractor on campus. It was actually purchased used in 1933, so it is actually an antique. It is over 100 years old in some bits of it. Below it is the hot water heater, or the 16-inch reflecting telescope at RLM. This is the one I've been using since I was a student and have now been running public viewing on for 20 years, unbelievably. But of course, if you want to get away from the city lights and actually see something besides what you can see from the middle of Austin, there are a couple other really good resources. So I have to put in a big plug for the International Dark Sky Association, who has certified many places in Texas as dark sky locations, including some within fairly good driving distance of Austin in that map down there. And then, of course, I have to call out the McDonald Observatory out in West Texas, if you're willing to take a drive. Some of the best dark skies in Austin. We have public viewing programs, and I think between 9 and 12 public viewing nights on one of the big telescopes if you can get tickets. And so the website's down at the bottom will give you information about all of those things.